Hello. Today we are going to cover the independent samples t-test. This is a brand new inferential test for you. It's one of my favorites, and hopefully you're going to like it as well. So before we learn this new inferential test, let's see if you remember what do we use a one sample z-test for. Do you remember? So from now on, what I want you to pay attention is that every inferential test has a particular use. So there's no one test that can possibly cover all possibilities. So for a one sample z-test, we only use it when we comparing a sample to a population mean. But what can be difficult? Okay, try to think, is it easy to obtain a population mean, especially if your population of interest is a very large one? So as you can imagine, a one sample z-test is not a very frequent use test, simply because the majority of times we do not have the population statistics parameters rather. So we rely on other tests to pretty much infer about them. Okay, because remember, inferential statistics is about inferring. Okay, so no longer inferential statistics deal with the average and the mean. I mean, we do use the average and the mean to calculate. As you're going to see, all the formulas contain the mean, standard deviation, and all that. As said, but those are means to be used to infer something about a particular group. Okay, where in descriptive statistics we were using the mean and the standard deviation to pretty much understand the characteristics of a particular group. So again, this is the formula for the z-test. Okay, so you have the sample mean, which is the x bar, minus the mu, okay, which is the population parameter, which is the proper term, over the population standard deviation divided by the square root of n, which is our sample size. All right, so what we're going to cover today. Our main goal today is going to be to, first of all, you to be able to understand what is an independent samples t-test, when do we use it, what is the difference between an independent samples t-test and a dependent samples t-test, okay, because they sound similar, but they're actually very different tests. The only common thing is that we compare two groups, otherwise they're completely different. And of course, how to use SPSS to compute both of them, okay? So, two samples, okay? So now we no longer have a population, right? Because as we said, it's very difficult to obtain information about a population, so it is way, way easier, okay, to compare two different samples, okay? So this is what we're going to do, okay? And I think the best way to describe it is by giving an example. So I'm going to read you the example and we're going to analyze it step by step, because when you're doing your homework this week, this is what I would like you to do, okay? So it says right here, if I can follow along with my mouse right here, it says Dr. Armstrong, a researcher at CSUF, is interested to see how blood doping can impact the cyclist's overall time on a 30-mile course. He selects two samples consisting of 10 cyclists each. One sample he provides with the EPO, a hormone used in blood doping, and the other sample receives no treatment. Okay, so this is your placebo group. Okay. After treatment, he records each participant's overall time in minutes. And then the question is, how could Dr. Armstrong identify whether or not there was a significant difference in overall time between the two groups? So now I want to pause for a minute and I want you to pay attention and try to identify rather what's important here. So apparently we are having two groups, okay? They're going to be tested on the same thing, which is a 30-mile course, okay? Each group consists of 10 cyclists, so this is going to be your N, okay? So group number one is going to have 10 cyclists. Group number two is going to have another 10, okay? So your total N is going to be 20 between the two groups, okay? Now, what is the what are we trying to identify? What the researcher here wants to find out? He wants to see if there's a difference between the two groups. So what does that mean? Okay, do we care if the doping group is going to do better? No, it doesn't say that. Okay, what he says is if there's a difference between the two groups. So since we're simply looking for differences, that means that this is going to be a two-tailed test. Okay, if the researcher would state something he wants to see if the doping group will perform better, then that would be a one-tailed test because we would only be interested in the positive side of the curve. But since now he's only simply looking for differences, it's going to be a two-tailed test. Okay, so be very careful. When you have a word problem, try to find the important information, circle your N. If I'm giving you standard deviation, circle that. Try to see the question. Is he's looking to, for differences? Is he's looking for an improvement, drop in time, or whatever that may be? Okay, that's going to guide you in order to make that educated decision. Is it going to be a one-tailed test or a two-tailed test? Because when you use your table to find the critical value, as you can see, the numbers differ greatly. Okay, besides that, when I'm giving you an alpha of 5%, if you're having a two-tailed test, that means that you need to split that alpha. That means 2.5% is going to go in one tail and 2.5% in the other tail. Where if you were checking and if you were running a one-tailed test at an alpha of 5%, that means all that alpha is going to go in the tail of interest. Okay, so be very careful because that will affect your final results. Because if you get the wrong critical value and you're comparing it with your test statistics, you might be thinking that you're rejecting the null when in fact you were not, simply because you obtained the wrong critical value, thinking that it was a two-tailed test when it was actually a one-tailed test. So pay attention to those little details. All right. So independent samples t-test would be, and this is how it works, right? So we have our doping group, the one that's going to receive the treatment, the other group, they look like little dwarfs, okay? It's going to receive no doping, okay? And we are going to actually compare them, right, on the same variable. They're both going to compete 30-mile circuit. And then depending what differences we find, we're going to say, well, that one group is better than the other, or maybe there's no differences. So remember this, we're going to go step by step. Every single inferential test, I want you to follow the exact same guidelines, okay? First of all, we're going to always identify the significance level. I can guarantee you the majority of times, even if I don't mention anything, assume that it's going to be 5%, okay? So majority of times for this class is going to be 5%. When we're going to use something different than 5%, well, try to think about it. If you were working in a pharmaceutical company and you're getting ready to release this very powerful drug, okay, I don't think you would want to release it if you were 95% sure that it's going to work and you have a 5% probability that it might kill somebody. Okay, so apparently there's certain situations that we want to be a little bit more sure than just 95%. But for humanities, when we're just simply studying behavior changes and stuff like that, 95% is pretty good. Okay, so we're gonna identify that. Oops, did I go too fast here? Yes, I did. All right, so we always gonna identify the significance levels. We always gonna go ahead and compute our appropriate test statistic. In this particular case, it's going to be a t-test. We always gonna have degrees of freedom that we need to calculate, and heads up, every single test has its own unique degrees of freedom, so it will vary for every single test. So that is something also that will affect when you're actually trying to figure out how to obtain your critical value that you're going to compare your t-test to the critical value to see if you're rejecting or not. And you're going to be using a t-test table. So this is a brand new table. I think it's an easy table to read. I will explain you how to read it. It's on the back of your book. Depending the version that you have, it might be 371. I think this is from fifth edition, if you have fourth edition, it doesn't matter. You'll be able, all the tables are on the back of your book. I will also make a copy and post it on Titanium to right next to the Z table that you already have. Okay, so let's get started. Okay, so as we said, we're always going to have a 5%. And as you can see, this guy has an alpha tattoo on his back. So what do you think that means? He's pretty significant, isn't he? Yep, he got the alpha. All right, so check mark on the first one. Next, we're going to start to computing the test statistics, and we're going to have a brand new formula. How do you like this? This is a very, very beautiful formula, but do not have to worry. You're not going to use that. You're going to use something a little bit shorter. Okay, so not to worry. Your book has this formula inside. Please do not use it. You're going to drive yourself insane, and there's no reason for, because the problems that I'm going to give you, I'm gonna actually give you a different number to use for your denominator. So you can forget this large denominator, although all it is really is just pretty much the error for the two, the variability between the two groups, okay? And the top part, the x1 bar, is just the mean sample of group number one and the mean sample of group number two, because you're comparing to see the differences between the two groups, and then you want to actually correct for any variability between the two groups, okay? So instead of this, you are going to use this one, which is way, way easier, okay? So it's going to be x bar 1 minus x bar 2 over pooled standard deviation. So pooled standard deviation is a number that I will always give you, and it will say so. It's going to say pooled standard deviation is blah, blah, okay? So let's go back to our problem, but before we get there, we need to mention something about assumptions, okay? Assumptions are, in statistics, every time we have to run a test, we need to follow certain rules. Otherwise, our findings, they're not going to be accurate. So statisticians, they have figured out a way of how to try and make, I guess, the test as accurate as possible, because if you try to think about it, we're comparing samples and we're trying to infer something about the population, okay? So we need to be very careful when we're comparing groups to be uh, I guess, as close to the real thing as possible, to run our statistics in a way um, that we're not going to introduce any biases. So one basic assumption for the t-test, and please make sure you do know this one, okay, it's called the homogeneity of variance, okay? Homogeneity means being uniform, okay, and so having uniform variance. So what we're looking here is that the variance between each group needs to be pretty close with each other, okay? So the one group should not be very different than the other group. In other words, we cannot be comparing apples with oranges. And what do I mean by that? So try to imagine that you want to test this intervention that we're talking about, that you're giving people this EPO hormone and you want to see if they're being improved or not. But as you noticed at the very beginning, it was just a joke. You know, the one guy was like a pretty huge dude, and, you know, comparing it with a little dwarf, apparently that would violate the homogeneity of variance assumption, right? Because it just simply would not be fair. So in real life, if you were to test anything like that, you wouldn't, for example, go put a bunch of athletes in one group and then maybe go to, I don't know, to the philosophy department, or definitely not the kinesiology department, but maybe the psychology department, and get a bunch of students there and try to compare them against the athletes. Okay, that simply wouldn't violate the homogeneity of variance assumption, because you're not comparing two equal things. It would be very different if you just go out in the university, you select 100 people randomly, and then you split them into two equal groups, okay? Then you're not being biased if they're athletes, if they're just simply students or whatnot, okay? So usually in research, we always trying to be as unbiased as possible by taking into consideration anything that could affect our results other than our treatment. Okay, so we're trying to control for any other variable. So in this way, the variance between the two groups should be very, very equal. If it's not, SPSS actually will tell you that the homogeneity of variance is actually being violated. And then there's other measures that you can take to correct for that, or you're going to have to start over pretty much. But for this course, you don't have to worry about it. I just want you to know what the homogeneity of variance is. All right, so this is what we have from our example. So we have the control group. So again, the control group is the group that receives no treatment whatsoever, or placebo group if you want to call it. And there the mean time was 120 minutes. Then the people who received the treatment, which was their EPO hormone, they did 98 minutes. So this is the sample mean of the second group. And their pooled standard deviation is 8 minutes. Okay, so let's go ahead and calculate. This is our formula. And we're simply plugging in. So you're going to say group, the mean group of the mean value of the group 1, which is 120, minus 98, which is the mean of the second group, over the pooled standard deviation. Okay, now a lot of students usually ask, well, Georgia says, well, how do we know which one's going to be X1 and which one X2? Good news, it doesn't matter. Okay, so even if you switch these guys here, yes, you will end up with a negative score. But if you take the absolute value of this and you're comparing it with your critical value, then it won't really matter. The only time you're going to have to be careful is if you're having a directional test, but you will be able to tell because then it's going to be phrased in a way that you will know what you're comparing and what you're trying to obtain. You just need to be very careful when you're reading. But in a two-tailed test, really doesn't matter. Because it goes either way. So you're just going to compare your obtained statistics here with your critical value. So even if you put 98 minus 120, you would still get the same result. It just would be negative. Okay. So anyhow, if you do the math here, the obtained t-test statistic is 2.75. So we're done with step number 2. So now we need to obtain our degrees of freedom. And what are those degrees of freedom? Do not bother your mind. It is really based on a very crazy quadratic formula. And what it takes into consideration really is how big your sample size is, what are, the probabilities and error. So it takes a lot of assumptions put into a formula, and that is the reason why every single t-test, it has its own unique. So for example, this particular t-test usually can be used for sample sizes that they're even less than 30. So apparently we need to make corrections for that, because remember, the smaller your sample is, the more likelihood that you're going to be a little bit further away from the true population mean, okay? The larger the sample size, the more confident we can be, okay? But if we have very large sample sizes, there would be no reason to use this test to begin with. So anyhow, so the degrees of freedom for this particular test is going to be the sample size of group 1 minus 1 plus the sample size of group 2 minus 1. So essentially is your total n minus 2, okay? So remember, we had 10 cyclists in group number 1, so we take one away, and 10 cyclists on the other group, right? So we got 9 plus 9, 18 degrees of freedom. So now we need to use our brand new t-test table to obtain the critical value, right? All right, so brand new table, not this one, this one. Now, a few things here. Let's get it a little bigger. Okay, you're going to notice it says on the very top, and make sure that you always pay attention to that. Identify if your test is a one-tailed test or a two-tailed test. Okay, so that's the first decision you need to make. So make sure you make that decision in order to be looking and reading on the right column. Okay, then you're going to be seeing your significant levels. So do you have an alpha of 5%? So you're going to be looking in the middle column right here, right? If you have 10%, that means you're looking, you want to be 90% confident, then you're going to be looking column number one. And this column would be if you want to be 99% confident. I can guarantee you the majority of times that I'm going to test you or I'm going to ask you to do your homework is going to be the middle column right here. Um, or otherwise, I will specify that I want you to look that critical value for that alpha, okay? Then on the left side here, you have your degrees of freedom. So as you can see, depending on how many degrees of freedom you have, your critical value will change, okay? So in our example, okay, we are having an alpha level of 0.05. We have a t-test statistic to obtain value of 2.75, and we know that our degrees of freedom are 18. So it's a two-tailed test, 0.05, middle column, degrees of freedom 18, and where the two meet, that is going to be our critical value. So for this particular test, our critical value is going to be 2.101, and we're going to comparing that with our test statistics, okay? So remember our obtained value from the test was 2.75, which is a lot greater than our critical value, which is 2.101. So guess what? We reject the null. Yay! That means that there are differences between our groups, okay? But the question is, okay, how different really are, how great that difference is. Is it a great difference? Is it a small difference, right? It's like the t-test, all it told us is that there are differences between the two groups, but we do not know how significant that difference is. Is like how different are they truly? So what we have is another test, okay? So that measures effect size. And this is Mr. Jacob Cohen, who actually invented the effect size, or Cohen's d, as some of you might have heard it. Oops. And all it is, you take the sample mean of the one group, you subtract the other one, and you dividing that with the standard deviation, okay? So the greater the result you will take, because imagine um, if you have a great difference in your numerator and your variance here is very small, most likely, right, your effect size is going to be pretty large. So that means the greater the differences between the two groups is going to be simply on the differences, since the variance is not really affecting it, okay? So in this particular case, we had 120 minus 98 over 3.75, and we get a negative 5.86, which is an amazing effect size, because this is how you evaluate the effect size. Very similar, if you remember, the Pearson's R kind of values. So if you have point 2, it's a very small effect size. 0.5, you know, nothing great, medium. Anything 0.5 and above, it can be considered pretty significant, okay? All right, so we just followed all those steps, right? We were able to state the null, state the alternative, we set our alpha level, we selected the appropriate test, we computed the test statistic, we determined the value needed to reject the null, and we compared our obtained value to the critical value, and we were able to state our results, okay? Now, I really want you to remember those, okay? You might see a short answer question on the final that says state the steps of the hypothesis testing, okay? So I would definitely know this, guys. And now let's do one more example, okay? So here, let's read it. You're a researcher in the health science department at CSUF. You're conducting a study looking at how diet can impact physical endurance. You're specifically interested to see if people with a vegetarian diet will be faster, slower, or no different from who eat meat when running a mile. You choose 8 vegetarians, group number 1, and 10 meat eaters, group number 2, and ask them to complete a mile run as quickly as possible. You gather the following information, and you have the mean of group 1 to be 6.86, standard deviation 2.3, group number 2 6.48 minutes, standard deviation 2.28, and we have a pooled SD of 3.42. Okay, once again, so it's really easy to identify. You have again 10 people in each group, right? Actually, you have 10 people on the meat eater group, 11 on the vegetarian. So these are your ends, right? And then as far as identifying if it's a one tail or two tail, this is where you need to look. It says, will they be faster, slower, or no different? So what would that be, right? So if we're faster, that means positive side. If they're slower, that means on the negative side, or no difference or both sides. So guess what? This is a two-tailed test as well. So here, if we only had the faster and not the rest of it, would be a one tail, positive tail. If we had the slower only, would be on the negative side, right? And no different would be the two-tailed test. But now I'm telling you all of it, so you can count pretty much for we're simply looking for differences. So this is what the test is telling you here. So do not get confused and make sure you read all this, every single information on every single word problem to make that educated decision. So again, we're going to state the null, okay? So the null will state no differences as always. So there will be no differences in average time between those who are vegetarian and those who are carnivores, right? So now that actually we're covering a stating hypothesis again, I noticed on your last homework, a few of you, they were explaining to me what it means and they were using question marks. Will they be there differences between the two groups? Remember, affirmative statements, we never question. If we question, that means we're having doubts about what we're trying to do. Null hypothesis always states no differences. Alternative hypothesis either will have a direction or no direction, but no matter what, okay? And in this particular case, since we know it's going to be a two-tailed test, that means we're looking for differences. We need to state our alternative to depict that, okay? So if I would see here a direction, I would count it as wrong, okay? So the alternative for this particular example is going to be there will be a difference in average time between those who are vegetarian and those who are carnivores. So an alternative hypothesis that would state that the carnivores will be faster than the vegetarians, that would be directional, but in this particular case would be wrong because this is not what the researcher is looking for. So pay attention. Our alpha level, once again, is going to be 0.05. Our formula, we plug in the information, right? Remember the one group, the mean of the one group was 6.88, the mean of the other group was 6.45, and the pool standard deviation was 3.5, okay? Our t-statistic is 0.12, okay? I would definitely try to do those without looking at the answer, so give it a shot on your own to make sure that you're able to plug in the information in the right place. Calculated degrees of freedom. You had 11 vegetarians, I believe, and 10 carnivores. So that would be 21 minus 2. That is 19 degrees of freedom. So we're good. We're pulling out our t-test. We are running a two-tailed test, 19 degrees of freedom. So right here, 19 degrees of freedom. At a 0.05 level of significance, we see that the critical value that we need to compare a test statistic to is 2.093. Okay, so there we go. Now let's compare the two. Well, this is our test statistic or the obtained value as it is called. And this is our critical value. Guess what? Our obtained test statistic value is way smaller than the critical value that we're comparing it with. So that means that our results are not significant. We cannot reject the null. That means we fail to reject the null. Thus, the final conclusion is that there's no differences between the two groups, right? So that's how you would state your results, okay? Dependency test. Okay, so as you can see, what do you see here? You see twins. Okay, and there's a reason for it. So paired, that is another way that a dependency test is called. So you might see it as paired samples test or dependency test. These are just similar terms and they refer to the same thing. So what is the difference between a dependent samples test and an independent samples test? As the word implies, independent means that the one group is independent from the other. Okay? Dependent, that means that group number one is dependent on group number two, and usually the reason that they are dependent is that they have some kind of relationship. The majority of times it's going to be a pre and post test. Okay? Meaning that you're examining the same participants twice. So maybe you're having this really cool intervention and you want to find out if it's working. So you gather a bunch of people, you test them before your intervention, then you go ahead, you perform your intervention, and then you measure them again. And if you see a difference between before and after, you can assume that your intervention is working, assuming that you held everything else uh, under control and nothing else played a role into obtaining those differences. So let's do an example to see how this differs. So again, the blood doping example that we did before, we're going to gather again 21 cyclists, okay? But this time, actually, we're going to measure them before, and then we're going to go ahead and give them the EPO hormone to all of them, okay? And we want to see if there's a difference between before they receive the EPO hormone and after the EPO hormone, okay? All right, so this is our going to be our before and after. So apparently this how the guy looked before he received the EPO. Okay, yeah, so he was this skinny little twinky little guy. We give him the hormone, right? We put him on a bike. He did his run. Okay, then we inject him with the EPO, and that's what happened right here. Okay, so we want to see if our EPO hormone actually works. Once again, our alpha, our significance level, okay, zero point zero 0.05. This is a new formula, which, like you do not have to memorize and you do not have to use, okay? So, for the dependent samples to test, you're only going to use SPSS. I do not want you to test. The only thing that I want you to know about the dependent samples to test is how to read an SPSS output and what is the difference between an independent and dependent samples t-test. So you might see a bunch of questions on the upcoming test that will ask you what is the difference between a t-test and dependent and independent samples t-test. Or I might give you an example and I will ask you to identify the type of t-test that it is. So yay, okay. But anyhow, once again, the dependent samples to test examines exactly the same thing. You comparing the before and the after mean performance, you're adjusting for any possible error, and you're done. So apparently, if you're receiving a large t-value, most likely that means that your results are significant indeed and that your intervention is working. Now, the next thing that I want you to know is how do you properly report an inferential test, okay? So as I told you before, inferential test always going to have degrees of freedom. So the proper way of reporting your results, either being a research paper or for your homework, is going to be T, which is the type of test that you're having. The 18, which is your degrees of freedom, you always place that in a parenthesis. Geez, okay, I do not want to do this. Sorry about that. So here normally next to the t-test, if you ever go to grad school, they also going to ask you to put your significant level. So normally here you should have one more parenthesis and should look something like t parenthesis 0.095 parenthesis degrees of freedom equal to your obtained value, and then you state your significance level. For this class, if you just give me your inferential test, like is either being a t-test or an f-test that we're eventually going to do, your degrees of freedom, your obtained value, and if you obtain significant results or not, I will be a happy camper. Okay, so here pretty much what you're saying with this p less than being 0.05, this means that you got significant results. Okay, because try to think about it. If your p-value is less than 0.05, that means you fall into that critical zone. Try to imagine the normal curve, right? And you set aside 5%. And that means that you're falling less than 5%. So you're above 95% sure that your results are not due to chance, because remember, we only were willing to risk 5%, and that is what our significance level is. So you were willing to risk 5% to be wrong, and since you rejected the null, that means you're at least 95% sure. So your p level anytime you reject the null is always going to be less than 0.05. So if your results were not significant and you failed to reject the null, you would state your result as p greater than 0.05. Okay, so just be careful. You might see an SPSS output, and I'm gonna have you to read the p-value, and you would need to observe and state that it is significant or it is not significant. So always remember, anytime that your p-value is less than 0.05, your results are significant. Anytime p is greater than 0.05, that means your results are not significant. All right, so let's wrap it up. Today you were introduced to the t-test, and it came in two flavors. So you had the independent samples t-test and the dependent samples t-test. Usually the independent samples t-test compares two completely different groups, but remember they have to follow the homogeneity assumption, which means that the two groups, yes, they're different from each other. It means you're using different people, different participants, okay, but they should be pretty equal, okay? So your groups should be comparable. So you might be, say, comparing health science students with psychology students on math performance, okay, to see who's doing better in math. But you would not be comparing, say, a math major student with a psych student. It just wouldn't be fair, okay? So again, you're comparing different people, okay, and you simply want to see if there's differences or if one group is better than the other one or not. With a dependent samples t-test, okay, you're comparing usually the same people or people who share some kind of relationship that will affect the final outcome, like let's just say couples, okay, usually couples, they have to match. So that would be independent samples t-test if we were to compare them in any way. So once again, the majority of times though, it's going to be you comparing people over two different time intervals. So it's going to be before a treatment, and then you provide them with an intervention, and then after the treatment, and you want to see if there's a difference before and after the treatment. Okay, so that is that. Okay, good job, everybody. You're gonna hear probably one more lecture from me, and that's gonna take you over and guide you with SPSS and going over how to run a t-test. So